Sets together with the operator complement, union and intersection define a special class of Boolean algebraic structure. Essentially, complement works like a NOT operator, intersection works like an AND operator, and union works like an OR operator. So we can take the rules that we had from Boolean logic and convert them for set theory as well. So these are some instances of this. So one thing I would ask you to do is compare this to chapter 1. Compare this to Boolean logic. That way you can see how they are related to the Boolean logic. So the first set of laws are identity laws. So if I take A intersection with the universal set, this is same as A. You should see that this is similar to A, and true is same as A. So essentially the universal set works just like the truth value in Boolean logic. The empty set works like the false value in Boolean logic. So A union the empty set is A. This is similar to A, or F is same as A. In other words, the empty set works like the Boolean formula false. Here are some other examples of set identities. I won't be going through it one by one here. What I want you to do is go through each one of them, and we'll discuss more about this in class. So let's look at one example. Here we want to say A union B, complement of that is same as A complement intersection B complement. To show this, we can use one of the following ways. We can use the fact that two sets are equal if and only if the first set is a subset of the second, and vice versa. We can use set builder notation, like define what A intersection B is, what a complement is, etc., and then show that both of these set builder notation get us to the same value. We can use membership tables. This is basically just like the truth table that we use for Boolean logic. Let's look at the first approach using set builder. So what is A union B complement? Well, let's first look at the fact that the last thing that we are doing is the complement of something. So I can define this as the set of elements X such that X is not in A union B. Now I can define what it means for something to be in a union. So first of all, I have taken this not outside. So it is not of X is in A union B. X is in A union B is same as X is either in A or X is in B. Then we can apply De Morgan's law to get that X is either not in A and X is not in B. And we can take this further one step at a time to show that this is same as A intersection. This is same as A complement intersection B complement. The way we can build this using membership is basically just like a truth table. So unlike truth table, which had the true false values for each one, we are basically going to say let's take an element X and see where it falls. So the first row is when it's in both A and B. Second row is when it's in A but not in B. Third row is when it's not in A but in B. And fourth row is it's not in either. For each of them, we can write the corresponding uh, entries for each row. So if the element is in A, that means it's not in A complement. If it's in B, it's not in a B complement. So if it's not in A complement and B complement, then that means that it's not in their intersection. Likewise, if element is in A, element is in B, then it is in the union, and therefore if it's in the union, it's not going to be in the complement. Now what we want to do is we want to make sure that these two columns are identical. If they are, then the equivalence that we are trying to show is valid. A few more operations with sets. We can generalize union to a collection of sets. So we can have sets A1 through AN, and we take union of that, and that's going to be represented by this operation. We write a big Q from I is equal to 1 to n of AI, and essentially this will contain the union of all elements in each of these sets. We can generalize intersection in the same way. So intersection of n different sets A1 through AN is represented by this notation or this notation as a shorthand, which is intersection from I equal to 1 to n of set AI, and this will include only the elements that are in all the sets A1 through AN. Once again, we have reached the check before you go ahead slide. The key thing I want you to get out of this is the relation between the set identities that we discussed earlier and the tautologies or proof rules that we looked at in the earlier modules. The relation is straightforward and as expected, and if you try to prove the set identities, essentially the proof would be very similar to what we did in the earlier modules. We have reached the end of the module, so I want you to go ahead and do the review quiz for this module.